See, this is a reinforced concrete pipe. In the professional world, it is referred to as an RCP. This is a 36-inch RCP, okay? This is a box culvert. These are already being made. They've been made for a very long time. These are everywhere. Pretty much anywhere you've ever seen a drainage system in a ditch, next to your house, going down the highway, the interstate. The bigger the drainage need, the bigger the pipes, okay? So, from my own personal professional experience, the most common sizes of these pipes are 18, 24, 36, and 48 inches. Okay, we still go by inches here in the United States. If this was going to be implemented in, say, other countries, we would obviously, the idea remains the same. You're going to want to use existing pipe sizes because you can't come in with an outsized pipe and try to, just connect it to another one. It needs to be these sizes. It needs to be these commonly already produced sizes, so we don't have to re-engineer a pipe. We can just use what's existing, okay? So, for our example, we would use 36-inch RCP piping, and we would use a box culvert. And this one measures, let's see, it is 12 feet tall by 8 feet wide by 16 feet long, okay? The box culvert would be used to house our tank, okay, where everything is going to take place, okay? This is going to be essentially the hub of where the action takes place, okay? As you can see on top of here, it's a nice flat area made out of concrete, solid. These are reinforced. They're made, you can look up their standards on let's see, cmex.com, for example. I don't want to go over them all here. I don't want to waste too much of your time. So anyway, like I said, this is already being used. It's a very strong platform to use. So it's one that's been tested in the field. We have plenty of data to go off of, and we know that it can sustain long-term use because it already does. And the proof's in the pudding. If it already works, it's going to keep working. We know the lifespan of these pipes. We know the lifespan of these box culverts. So we can very accurately predict how long they're going to last and how much exactly everything's going to cost. So the tank will fit inside of our 12 by 8 by 16 box culvert, and connected to that pipe will be these RCPs. Other commonly used materials for piping is metal and plastic, okay? A CMP, corrugated metal pipe, that's another one. Same sizes, the sizes remains the same. Sometimes the material changes for the need of the civil engineering, whatever's going in, maybe cost reasons. Some places you only need plastic because it's simple ditch draining. Some places you need concrete because you need to be stronger, and some places you need metal because you need to be even more stronger. Or maybe just the availability of the material at the time, okay? So like I said, recap real quick. CMP, RCP, and CCP. CPP. CPP, corrugated plastic pipe. RCP, reinforced concrete pipe. And then CMP, corrugated metal piping. Okay? Like I said, these are all things that are already in place, okay? So, we know we're going to use solar energy. We know we're going to use a tank. We know we're going to use existing piping. So how does this all come in and work? Well, this is the fun part. So I have my model here behind me, and I'll bring it in here and play in a second. Actually, I'll bring it in right now. Okay, so here is a example of how this is going to work. Okay, this is the inflow side. Okay. This is the inflow side, okay? This is longer than the outflow. Like I said, this is going to be right at the source of reintroduction, okay? So the outflow is essentially just putting the water that we treat back into the system, okay? Why is the inflow so much longer than the outflow? Well, because this is our first step of filtration, okay? We will have a series of filters in here, starting larger and going much smaller to remove at the beginning larger debris like trash, like those 6-pack bottle holders I was speaking of. Okay, they'll remove large items like that. And as the water flows through here, the filters are going to get smaller and smaller and smaller, eventually small enough to remove things like oil, okay, things like cleaning chemicals, pesticides, things like that. Okay, we're going to go large filters all the way down to small filters. Okay. Next question is, well, you have your solar energy. That doesn't have anything to do with filters, so what's the point of solar energy? Well, inside of the tank that I've been speaking of, secret revealed, we're going to have copper coiling that goes in at a space of 3 feet apart. So remember, this is a 16 feet long by 8 feet tall by 12 feet wide. Okay, so we're going to have a tank that's roughly 12 feet tall, 16 feet long, slightly smaller to fit inside of our shell, our box, our concrete culvert. At a space of 3 feet on both top and bottom, copper coils are going to be run into the tank. They're going to remain 3 feet extended from the bottom. As the bottom ones come up, they will remain 3 feet extended from the top. So that all coils at all time are at a minimum of 3 feet apart to create equal heating of the water. That's right, I said heating. If you're going to want to render water viable to drink, what do? In a survival situation, you heat it. You boil the water. If you boil the water, you can drink it and you can survive. It might not taste good, but you can survive. It pretty much kills off everything else that's in it. So, the solar paneling is on top. It collects energy from the sun, transfers that energy into electricity that heats the coils, a process called induction. So through this induction, we heat the coils, which in turn heats the water to a temperature of 212 degrees. As it reaches that temperature, it then reaches the outflow pipe, outflows into the natural water system, and is rendered safe. It's safe for you to drink. It's safe for you to drink. It's going to be safe for animals to live in too. Well, sometimes, Chris, it's cloudy and the sun doesn't come through. You're right. So attached to this concrete box culvert, which will also be underground, will be a battery bank. Roughly 10, 12 volt batteries, like ones you put in your car. They will be deep cycle though, which is meant for long-term storage. And sometimes it's not always raining. We don't always have constant water flow through these pipes because it's, like I said, it's a drainage system. When there's nothing to be drained, then there's nothing to be heated. Okay, this will all be monitored and run by software that we will acquire from an outside service. When there is no water to be heated, the solar panels will charge this battery bank and keep it for on cloudy days, for nighttime, for any time that the sun is not viable, because I guess the most time you're going to have your biggest water flow is going to be during a storm. And during a storm, there's not a lot of sunlight because there's a lot of clouds usually. So we'll have these battery banks to power this whole operation when the sun is not available. Another key factor is that a lot of times, for example, if this was situated at the bay and we're draining water from, here in Spring, Texas, if there's a storm here in Spring, Texas, Tomball, Texas, there's might not be that storm down in Galveston where it's being drained into the bay. So just because there's a storm present doesn't mean that the SWTT isn't going to be gaining solar energy at that time because that storm water travels a long way. All right. Now this will be buried underneath the ground, and like I said, we're going to be using existing infrastructure, so 30-inch, 48-inch piping. Using flow rates, we're going to manage this system, okay? which can be derived by mathematical equations, okay? So the inflow is going to have to be the standard size, whichever size we're connecting it to. The outflow can be whatever size we want it to be, okay? Through a shifting of this either up or down, this one up or down, we can control flow rates and the size of this piping, okay? Water is going to continue at the same speed, essentially. We can slow it down by enlarging a tank, and we can speed it back up or slow it down by either making this larger or smaller, the outflow. So using our flow rates, we're going to be able to control how long that water sits in the tank, which needs to be just long enough to reach 212 degrees. Here's another example. The water on the left of your screen is flowing at the same rate. Flowing in at the same rate as the one on your right. However, as this area condenses, it speeds up.